So I was talking about this table before my recording got cut up. So let's talk about this. So when you set up this freezing temperature or vacuum temperature, okay, so you can control the chamber pressure, that is the pressure outside of your vial. So especially the vacuum pool established in the chamber, established condenser area of your freeze dryer. Okay, so at that temperature, minus 45, actually the vapor pressure that's established inside a vial where the sublimation will take place is actually much higher. The vapor pressure is much higher than your chamber pressure outside. So that is a strong gradient that's established, okay, at that low temperature. If you increase the temperature, okay, again, it becomes higher vapor pressure, and maybe minus 40 degree, 96, and the outside could be 24 millitorr. Okay, so as you increase the temperature, you can see the vapor pressure is significantly increasing. Okay, so maybe minus 30, minus 5 all the way. It's at 30, 13. Okay, compared to outside 753. So there's a definitely big gradient established between the vapor pressure inside a vial and the pressure of the freeze dryer chamber. So that's how the vapor will travel from the vial to the outside condenser area. Okay. During the primary drying stage, the vacuum pool will remove the crystal, water crystal, the water vapor from crystal through sublimation, right? So that's the main function of primary drying, is to remove the pure ice that is located in the ice channel. Yes, through that sublimation. That's the process. So below the glass transition and eutectic melting temperature, the interstitial space is solid. That's the temperature you want to do the freezing and then vacuum drying. If you do the primary drying at the higher temperature, then you will lose everything. So everything will collapse and come out, right? So you don't want that. So above these critical temperatures, the interstitial space is a fluid that cannot support its own. So when the ice is removed and collapse occurs, so you will lose everything. So you don't want to do the primary drying at the higher temperature. So you need to know where these temperatures are located: glass transition and eutectic melting temperature. Okay, otherwise you will lose all of your drug. So if that happens, you may see something like that, collapsed cake. So cake is totally disappeared. So then you don't know where your drug is, right? So you don't want this. Okay. So during the primary drying, most of the water is removed, okay, 5 to 10% from the product at this stage, and so from the product evacuate through below 0.1 torr, okay, vacuum, which sublimes ice solvent to vapor, which then condense on the colder surface. Okay, so during this period, the temperature of the product should remain slightly below its critical collapse temperature. Of course, that's similar to the eutectic or glass transition temperature of the product. Okay, so that's very important. So you need to know what those temperatures are. So once the primary drying is done, you will do a secondary drying to remove the leftover water, so maybe residual water from your drug. Okay, so there will be a secondary additional drying step. Okay, so to do the additional drying, you have to use a higher temperature, okay, to establish a higher vapor pressure inside your vial, of course. So secondary drying actually starts during the primary phase, but at an elevated temperature. Okay, so you saw that, if you elevate the temperature, you see what happens. So you get higher vacuum pressure, so you can pull more water vapor out from your drug. So that's how you can do the secondary drying, right? So that's what happens. Okay, so typically done in maybe 30 to 50 degrees in Celsius. It's done at the above melting point. Okay, so that's to remove more water crystals during this time. So the moisture content is in fully dried product. Once it's all dried, it's typically less than 0.5 to 3%. Okay, so less than 1% is actually ideal. In most cases, the more dry the product, the longer its shelf life is, because if you remove water, there will be less likely hydrolysis will take place, so your drug molecule will stay stable for a longer period of time. So the more water molecules removed, your stability of the drug will be better extended. That's what it means. Okay, so once the secondary drying is done, then actually you can stopper it, unless you want to maybe backfill your vial with maybe stable gas, like maybe nitrogen, if you want to. Okay, so you can maybe fill the vial with stable enough gas, or you can just lower down your stoppers, which you are probably usually sitting on top of your vial mouth, right? So there are normally collapsible shelf, so the shelf or plate located above your stopper will lower down. That's how your stoppers will be placed in and sealed up. Okay, so lyophilized drugs products are extremely hygroscopic. Hygroscopic means that they love to bind with water because they are all dry. Okay, so you want to remove water. You want to remove the possibility of getting water back into by seal of your vial, primary container. Okay. So free dryer is normally configured with a stoppering capability, meaning there's a means of placing the stopper all the way in your free dryer. Okay, that's normally by lowering down the top plate on top of your vial. Okay, so typically stoppering is done on vial with partially inserted stoppers because that they are loosely sitting. Okay, the shelves are collapsed. Okay, this shelf is collapsed to this down. That's how those shelves will place in, push in the stoppers. That's what happens. Okay. Okay, so this is a kind of a monitoring of your freeze drying process. There's a temperature or pressure on y-axis, maybe time on x-axis. You can monitor maybe pressure, product pressure, or shelf temperature or pressure. Yeah. So they'll be shown up during your freezing drying cycle. Okay, maybe time 0. So if it's a temperature, it comes down significantly. So probably it's the shelf temperature. That's freezing, right? And then after freezing is done, you will heat up during your primary and secondary drying. Okay, that's how you can establish the higher vapor pressure, right? So that's the shelf temperature change. And then if it's maybe it's the is that pressure change? Yes. So there's no pressure applied during the freezing process, of course, freezing or annealing, right? And then the pressure is engaged when the vacuum step is starting. In this case, maybe after 6 hours of freezing is done, you're starting the drying process, primary drying. Okay. And maybe the secondary drying after that. And then this is maybe the product temperature. So the shelf temperature, of course, is colder. So product temperature follow the shelf temperature. So it's getting down, it's frozen. I don't know where the eutectic temperature is, glassy melt temperature is, but it's going down much further. Okay, and then once it's all frozen through primary and secondary freezing process, and then the vacuum is pulled, and then you are heating up a little bit to get the drying done. Okay, so shelf temperature going up high and product temperature going up, following that as well. During this process, pressure is established, so drying takes place, and then primary drying, maybe secondary drying after that. So that's what happens during your freeze drying process. Okay, the principles of thermal analysis. So in order for you to develop or come up with the best freezing drying conditions, so you need to know all those temperature conditions, right? Eutectic melt temperature or glass transition temperature or amorphous, melting temperature, all those things. So in order for you to understand, you need these, especially these two critical pieces of instruments. Okay, number one is called DSC, differential scanning calorimeter. May looks like that. Okay, So this instrument can analyze those melting points, because it will give you thermal characterization of your drug molecule under different temperature condition. Okay, so this machine will allow it to find out exothermic transition, endothermic transition reaction. So exothermic, maybe it gives up the heat to outside. Okay, maybe it's like what maybe from crystal to maybe liquid transition, or liquid to vapor transition, or maybe it's the other way around. Okay, endothermic is it's absorbing heat energy. Okay, so maybe that's what I'm talking about, from liquid to vapor. Okay, maybe it's the other way around. So, okay, so which one will give up the energy? So materials are absorbing the heat, then it's going to be melted, right? If the material is giving up the energy, that means it's energy giving up energy. That's exothermal reaction. Okay, so the DSC can characterize those transitions happening in your drug. Okay, so the machine itself, so it looks like that. If you lift up this cover, you may see something like that inside. So there are two holes where you sample, and there may be calibration mixture. So one is for sample, the other one is for maybe water, or your standard can be added, and they'll be analyzed. So measuring the amount of energy that is required to keep the sample and the reference material. So what one's reference material, once you sample at the same temperature through the phase changes. Okay, so what you're going to see is, you're going to see this kind of graph out of your DSC analysis. Okay, so what you see here, temperature change here, and then heat flow, what kind of energy is evolved or taken up, that's what you're observing. So if you bring down the temperature, freezing, okay, you see one big maybe energy release, okay, because when you are freezing your material, okay, so it's losing its energy, giving up the energy to outside. There's a point where the freezing will take place from maybe liquid to the crystal form. That's the freezing point. Okay, but if you do it the other way around, the melting point, okay, so from the frozen condition, when it melts, okay, so it'll maybe absorb heat, okay, and to become melted condition. So you can see something like this, the peak formations. The large peak at the bottom curves the sample freezing and giving up heat. See, from liquid to frozen state, so it gives up the energy, heat. Okay, the large peak in the top, the sample, when the crystallized sample is being melted, okay, so it requires energy to transit from the crystal to the liquid form, and that's what is shown up. So DSC can do this thermal analysis characterization. That's what this machine does. So by looking at these points, you can see what the frozen point is, melting point is, what that temperature point is. Okay, maybe minus 17, or this is about above 0, maybe 2 or 3. Okay, that's what it does. The shape of the peak determines what phase is present, and the critical temperature of what phase melts can be determined. So eutectic melt is observed as sharp, symmetrical peak. So that's the eutectic melt, very sharp and symmetrical peak, while a glass transition showing up as a shift in the baseline. So baseline is kind of shifted. Okay, so it's a glass transition. It's like a S-curve typically. That's what glass transition is. Okay. The alpha curve is a result of metastable glass phase, which was mentioned previously. Okay, so understand. So what you saw is also, the eutectic transition. Okay, so DSC is very valuable tool in the thermal analysis of your drug molecule. Okay, so critical temperature for these kind of phases are determined by the computer software. For the eutectic melt, the computer draws a tangent to the baseline. Okay, and leading to the peak here, and tangent to the leading edge of the peak. Okay, temperature where the tangent line in the C is termed as onset melt. Okay, onset melt. That's detecting melting temperature. Okay, offset, onset, offset. So that's how they determine the temperature right there. Okay, and for the glass transition, okay, so the computer tangent on the leading